Welcome to the next session, my dear friends. In the previous session, we were discussing about the sludge volume index. So what is the importance of the sludge volume index? So what is the significance of the sludge volume index? So to maintain the concentration of MLSs here, okay, so because the whole process of activated sludge process is dependent on the food to microorganism ratio. As far as you keep the food to microorganism ratio as a constant, more or less same value, the system will run in the same manner, in an equilibrium. If you change it, if you disturb the food to microorganism ratio, then the equilibrium of the system will disturb. So that is why, so to maintain this, because here what is happening, microorganism is moving from aeration tank to secondary sedimentation tank, and a new microorganism concentration is entering here. So this new microorganism concentration which is coming along with the influent water, sewage, so it will be lesser only, but we want to keep a proper value, so we need to raise it. So we need to raise the value. So in order to raise the value, so we need to bring some activated sludge into it. So the concentration, the amount of activated sludge needed, so the amount of activated sludge needed, which how much activated sludge you need to send back into the aeration tank, that will be decided by by this QU, that is this QU again decided by the sludge volume index. That is why the sludge volume index is very, very important parameter for a activated sludge process. Okay. So what is sludge volume index? Sludge volume index, we denote it with SVI. Okay, we call it as SVI. So this is the space occupied in ml, the space occupied in ml by 1 gram of MLSs, by 1 gram of MLSs after settling, after 30 minutes settling, okay, after 30 minutes settling, from 1 liter of sewage sample, from 1 liter of sewage sample. So this is nothing but sludge volume index. So now what we do, we take 1 liter of a sewage sample from this aeration tank. 1 liter of sewage sample we will take. We will put that 1 liter sewage sample into it. So this is 1 liter sewage sample. So we leave it undisturbed for 30 minutes. After 30 minutes, so whatever the MLS is present here, that MLSs will settle down like this. So this is the volume in ml, and we can take the weight of this volume. So that is the ratio of the volume by the weight, that is nothing but SVI. So SVI is nothing but the ml per gram. So SVI is equal to what is the volume? What is the volume of MLSs in ml per unit gram? Okay, that is nothing but sludge volume index. Generally we keep this sludge volume index in between 50 to 150 ml per gram we will keep. Okay, so from where we are finding this sludge volume index? From here we are finding this. Okay, from here we are finding this. So here we are finding this. So what is this volume of the MLSs? Here this ml is space occupied in ml is MLSs volume. So MLSs is nothing but X. Okay, MLSs is nothing but X, right? What is the unit of X? It is milligram per liter. So the concentration of X is denoted in milligram per liter. Okay. So now here if I convert this milligram into gram, that means 10 to the power of minus 3 gram, right? 10 to the power of minus, I can write this as 10 to the power of minus 3 gram. So here liter in ml, that is 10 to the power of 3 ml. Okay, 10 to the power of 3 ml. So here x into 10 to the power of minus 6 gram per ml. Okay, so this is the concentration of X. This is the concentration of X. So concentration of X is equal to 10 to the power of, if it is unit, if I am taking it as unit, 10 to the power of minus 6 gram per ml. Okay, so now here if you look at this, this is nothing but 10 to the power of 6 by SVI. What is this? If I invert this, that means ml per gram. So that is nothing but what? If I am taking this side, if I am taking the whole thing, this side, on other side, that then it will become 10 to the power of 6 ml per gram. 10 to the power of 6 ml per gram. Okay. So this is called SVI, 1 by SVI. This is called 1 by SVI, sludge volume index. So this is equal to 10 to the power of minus 6 by SVI. Okay, by SVI. So now if I am taking here, this is, if I am taking it as XU. Okay, if I am taking it as XU, so this is X. This is X. Okay, if I am taking this as XU, then if you equate this to XU, that is 10 to the power of 6 by SVI. Here, so this is actually X. This is actually X. So if I am taking this on the other side, then it will become 10 to the power of 6 ml by gram. 10 to the power of 6 ml by gram. That is equal to, that means concentration of X is nothing but, it is not 10 to the power of minus 6. Yeah, here it is 10 to the power of minus 6. If I am taking to this side, then it will become 10 to the power of plus 6. 10 to the power of plus 6 ml per gram. Okay. So that is nothing but SVI. So now if I am equating this to this XU, so here SVI I am calculating it, SVI I am calculating XU is equal to 10 to the power of 6. SVI is what? SVI is ml per gram. Okay, this is ml per gram. So ml, again I can write this as liter, 10 to the power of minus 3 liter. So here I don't change it here, it is, leave it as SVI. So here it is mg per liter. This is mg per liter. If I equate the units on either side, okay, this will become 10 to the power of 6 again. This will become 10 to the power of 6. So this and this will get cancelled. So that means this SVI, what I want to say here is this SVI we are calculating from the concentration of MLSs here. Okay, this SVI we are calculating it. This SVI we are calculating it from the concentration of X here, and we are equating that to XU. That means indirectly we are equating XU to X using this SVI. Using the sludge volume index, we are equating XU and X. That is why, so this XU, how much XU is needed? How much XU is needed, that you will understand from the sludge volume index, which you calculate from the concentration of MLSs. So to establish a relationship between X and XU, we need the SVI, sludge volume index. Depending on this only, we can recirculate how much water and how much sewage I need to send into this aeration tank, that is QU. QU can be decided, okay, QU can be decided using this SVI only. QU is equal to QU by Q is equal to x by 10 to the power of 6 by SVI So using this relationship we can find how much sludge you need to send back into the aeration tank. So generally the value of this QU, ranges, or QU by Q, this QU by Q ranges in between 0.25 to 0.5. It ranges in between 0.25 to 0.5. Okay, so the important thing we need to understand here is XU concentration we calculate using the MLSS concentration, but sometimes if this amount of sewage or sludge you are sending here, it is less. Okay, so if you are sending less amount of sludge, then the concentration of the microorganism should be more. That means XU and X, if you compare XU and X is present in QI. That means the quantum of water which is coming as an influent is more. So that is why the concentration of X may be lesser. Whereas you are sending this XU from this activated sludge, where you are taking very little, you will be having more concentration. See, whenever I am equating this XU and X, I am taking 1 liter sample only. But here if you see, when in reality XU and X is calculated in the total amount of water, here it is equal. For 1 liter if you take, XU and X will equal. But if you are taking QI for X and QU for XU, then obviously QU is very less, QI is very high. So as the quantity is high, the concentration will be low. So quantity high means number of liters is more. Here number of liters is less. So that is why XU concentration in reality will be more. If you compare with the equal amount of water, then equal amount of sewage, then they may be equal. So that is why whatever the thing we have did here is with this sludge volume index. But here XU concentration may be more. In reality here XU concentration will be more. Approximately XU concentration ranges between 9,000 like that, like 9,000 to 12,000 mg per liter. 9,000 to 12,000 mg per liter. Whereas X concentration varies between 1,000 to 2,000 mg per liter. Okay, likewise they two vary. Okay, but how much XU we need to send, that you will decide from the X only again. So this is the importance of sludge volume index. So these are the different design properties of the activated sludge process. These are the different properties of activated sludge process. So what are the different kinds of conventional? See, this is why I have told you there are two types of aerations, that is a completely mixed flow type, and other thing is plug flow. Earlier, before invention of these complete mixed and plug flow, there are different ways of doing aeration. So those are called conventional activated sludge processes. We call them as conventional ASPs. So let us see what are the different kinds of conventional activated sludge processes are there. So conventional, I told you already. So the conventional methods and the latest methods are like this tapered aeration, okay, and stepped aeration. So using this complete mixed flow type. So all these things are latest developments in the conventional activated sludge processes. Okay, so here in conventional extended aeration, okay, stepped aeration, tapered aeration, and its modifications. So here extended aeration. So I have already told you what is meant by stepped aeration and tapered aeration. Extended aeration is when the food to microorganism ratio, okay, is kept lower. So we are keeping less food, more microorganism, and the detention time is kept more. So that means we are giving extended aeration. So which is not necessary that much of aeration we are giving. That is nothing but extended aeration. So that is not this kind of, that means here what kind of phase that will develop? Endogenous phase. Obviously endogenous phase will develop because food is lesser, microorganism is more, microorganism concentration is more, but it is not finding that much of food, then microorganism will eat each other. So because of which microorganism will die. So this phase is called endogenous phase. Okay, so generally it takes lot of time and also it is uneconomical. Okay, so but when we are not having any kind of primary sedimentation tank, treatment is not possible. You are directly doing activated sludge process treatment only. So in those cases generally we prefer this kind of extended aeration. Okay, so in extended aeration, food to microorganism ratio is kept small and aeration is provided the phase of microorganism is endogenous here. Okay, so these are the different kinds of aeration methodologies we generally follow. Okay, so this is all about the activated sludge process. Now, so we are so there are one more last concept, that is operational problems. Operational problems in activated sludge process. What are the operational problems? So during the operation, what happens? So what are the problems we face? So during the operation of activated sludge process. So this is a very, very important topic for the examination. Anyways, we'll do all the previous gate questions. You will get an idea on this topic. Operational problems of ASP. So the first one is bulking of sludge or rising of sludge. Okay, bulking of sludge and rising is one problem. Rising of sludge, and second problem is bulking of sludge. See, rising of sludge means the name itself says the sludge will rise. So in the secondary sedimentation tank, the sludge has to move downwards. So in the secondary sedimentation tank, the sludge has to move downwards, but instead the sludge will rise upwards. That is nothing but rising of sludge. So that sludge will go into the effluent again. So which we don't want. Generally, we don't want any kind of sludge in the effluent. We want sludge at the bottom. We will collect that sludge and we will send it to the sludge digestion tank. So this rising of sludge will be a problem during the disposal of the effluent. So that is why this rising of sludge is an operational trouble of ASP. Why this is happening is, if you don't properly maintain the food to microorganism ratio, the microorganisms are more and food is less, then what happens? I told you already, nitrogenous organic matter decomposition starts in the secondary sedimentation tank, because of which the nitrogenous material, whatever the, after decomposition, the nitrates, okay, so whatever the byproducts of the decomposition of the nitrogenous, phosphorus, sulfur material, so that precipitate will be very small. They may have a nature of rising. So because of less gravitational effects on it, so the rising of sludge will take place. So this can be controlled by controlling the food to microorganism ratio. Okay, so by sending more QR and decreasing the theta C, we need to send out the microorganism as early as possible. So we need to reduce the incoming sewage. Okay, we need to reduce the incoming sewage and we need to increase the QR, returning sludge, QU we need to increase. Okay, so by doing this we can control this rising of sludge. So here, if we increase more QR, okay, if you increase more QR availability here, that means if you are taking more sludge, listen carefully, if you are taking more sludge out of the secondary sedimentation tank, less microorganism will be available for nitrogen. Okay, so here whatever the organic matter that is present is nitrogenous organic matter. Okay, this rising of sludge is happening in secondary sedimentation tank because of the decomposition of the nitrogenous matter. To reduce the decomposition of the nitrogenous matter, from here we need to remove the microorganisms. To remove more microorganisms, we need to remove more sludge from here. So by increasing the returned sludge, one way we can control this, rising of sludge. And another point is, we need to kill the microorganism. So excessive microorganism concentration is causing this. To kill the microorganism, we need to create endogenous phase inside the aeration tank. To create the endogenous phase inside the aeration tank, we need to reduce the food availability for the organisms. How can we reduce the food availability to the organisms? By reducing the influent. So influent is bringing the food for the microorganism. By reducing the food, so we can reduce the concentration of the microorganism. So by that way we can prevent this rising of sludge. And third one is decreasing the theta C. That means endogenous phase. If you are creating endogenous phase, means we are indirectly we are reducing the mean cell residence time of the, we are directly killing the microorganisms, so the mean cell residence time is also decreases. So this rising of sludge can be prevented by increasing returned sludge into aeration tank Okay, so decreasing QI and decreasing theta C. So by doing these things, we can reduce the rising of sludge. Okay. So bulking of sludge means, bulking means what? Growing the size of the sludge. Growing the size of the sludge. Okay. So why this grow of sludge? That means depending upon the material. Okay. So depending upon the material. If you are having large number of dead cells. Okay. So if you are finding large number of dead cells inside the sludge which is present inside the secondary sedimentation tank, these dead cells will absorb the water and increase its volume. So that is nothing but bulking of sludge. Okay, that is nothing but bulking of sludge. Okay, so this can be reduced. Okay, this can be reduced by reducing the, can be prevented by decreasing sludge volume index. So volume, why we are reducing sludge volume index? See, if you are reducing sludge volume index means what? ml per gram. So this ml, if it is more, then we call this as bulking of sludge. So if you are reducing that ml, so that means what? So SVI decreasing means you are reducing the ml per unit gram. So that means bulking of sludge you are controlling by reducing the sludge volume index. Okay, by reducing the sludge volume index, and by increasing the pH. Okay, by increasing the pH. So by increasing the pH, so if you increase the pH, the bulkage of the sludge, so the bulkage of the generally the this sludge will be developing filamentous organisms. Okay, some kind of filamentous organisms which leads to this bulking of sludge. So those filamentous organisms can be controlled by increasing the pH. So by that way, so the filamentous organisms can be controlled indirectly. So indirectly we can control the bulking of sludge also by increasing the pH of the sewage. Okay, so and other things are also there, adding nutrients, addition of nutrients, decreasing food to microorganisms ratio. So these are some kind of preventive measures that we can take, okay, to reduce the bulking of sludge. So this is all about the activated sludge process. So let us move to the next topic, that is trickling filters. So next topic we are going to discuss is trickling filters. So this is all about activated sludge process. So we are going on to the next topic, trickling filter. Very simple topic, very easy to understand. Only one or two formulas if you understand, then those two formulas are sufficient for the examination. See, it is similar to the filter which we have discussed in the water supply, but only thing is here it is removing the BOD, there it is removing the finer particles and of dissolved ions and all those things we removed there, but here we remove the BOD. So trickling filter, it works on attached growth culture. It is a device which works on attached growth culture. Attached growth culture. Okay. So here trickling filters, generally it consists of a bed, okay, which is highly permeable. So trickling filter will be having a bed and it will be having a rotary arm which will distribute the sewage uniformly on this filter bed. Okay, these trickling filters are classified basically into two types. One is a standard rate trickling filter and high rate trickling filter. Okay, basic classification is a standard rate trickling filter, and this is a conventional trickling filter. Conventional trickling filter and high rate trickling filter. Okay, high rate trickling filter means if you do recirculation, generally we call it as high rate trickling filter. Okay, now here in standard rate trickling filter, there will be beds. Okay, generally it looks like this. The trickling filter will be having a rotary biological arm. If you look at the top plan, if you look at the top plan, there will be the biological arm. So this is the arm having nozzles. So this it will rotate when there is sewage enters into this arm. So when the head of the sewage is approximately 5 meter, at least 5 meter head if it is present, then the sewage will enter into this arm. This arm will rotate on the surface of the this bed, filter bed. So the filter bed, if you look at the cross section, so it looks like this. So how a normal kind of filter media looks, in the same manner it also looks. So this is the rotating arm. This is the rotating arm. So this is the filter bed. So this filter bed contains broken brick bats. Okay, so to allow air flow into it, so we generally use a material which will be having more voids, so that the sewage will trickle into these gaps. Okay, and it also allow the flow of air, so that the oxygen availability can be ensured. The oxygen availability can be ensured. Okay, so likewise, generally we will construct the trickling filter. So this is the arm. So this arm will distribute the sewage onto the top of the trickling filter bed, and we will collect the effluent somewhere. So this way we collect the effluent out of the trickling filter. Okay, so but if you look at the oxygen availability, in generally oxygen availability will be more at the top of the bed, because from both the ways it will get the oxygen, from the top and from the bottom, from the side. So all the ways we will get the oxygen at the top layers, whereas at the bottom layers generally the oxygen availability will decreases. Okay, so the decomposition at the top, it happens under more aerobic conditions, and if the oxygen availability, if it is less, okay, and also if you look at the food availability, so oxygen availability decreases to the bottom, and also the food availability, major food will be available on the top of the filter bed, and the food availability also decreases. So that means at the top oxygen availability is more, food availability is more. So that means their microorganism availability will also increases, and when you are propagating towards the bottom layers of the filter, food availability will be less, oxygen availability will be less, so endogenous phase will develop here, so that the effluent will be free from microorganism as well as free from the BOD, so that is why here the efficiency, here also we can get an efficiency of around 80% efficiency we can achieve in the trickling filter also. So here the rate of food removal, okay, in attached system depends on the rate of food or rate of BOD removal. So the rate of BOD removal depends on the hydraulic loading rate, how much loading you are doing, the hydraulic loading rate or the flow rate. Okay, the hydraulic loading rate, it depends on hydraulic loading rate, or we can call it as flow rate, and it also depends on organic loading rate, So hydraulic loading rate, organ loading rate, and what is the rate of diffusibility of the food and O2. Okay, so what is the rate of diffusibility of food and O2 into the filter bed, into filter bed, and what is the temperature we are maintaining in the trickling filter. So what is the temperature we are maintaining on the trickling filter? So on these factors, generally the rate of BOD removal the rate of BOD removal will depend in the trickling filter, okay. So here how to design a trickling filter, so let us see the design of trickling filter. So we are discussing first standard rate trickling filter, and then we will discuss the high rate trickling filter. So NRC has given an equation, okay. Using that equation we generally design the filter. So filter design is what is meant by filter design? Filter design is nothing but, so what is the surface area and what is the depth of the filter. Generally the depth of the trickling filter varies around 2 meter, 2 to 2.5 meter, the depth will vary. So here we need to fix up the surface area majorly, that is nothing but the design. So design of trickling filter. So design of trickling filter. Here there is an empirical formula given by National Research Council, NRC. So they have given an empirical formula to find the efficiency of the BOD removal. I told you the efficiency of the BOD removal depends upon the factors which I have told. Keeping those factors into consideration, NRC has given an equation for the BOD removal. Generally, what is the conventional equation we use to find the BOD removal efficiency? So efficiency of BOD removal, generally we use a formula, simple formula, that is Yi minus Ye by Yi into 100. This is the efficiency formula which we use. But what is the equation given by the National Research Council for finding the efficiency of the BOD removal of the trickling filter is 100 by 1 plus 0.0044 into square root of u. So this u is nothing but organic loading rate, where u is equal to q into yi by v into f. Okay, q into yi by v into f. What is q into yi by v? So q into yi is organic loading. It's nothing but organic loading in kg per day. Organic loading in kg per day. Very, very important. The units are very, very important because this is an empirical formula. So in empirical formula we need to remember the units, otherwise what happens, you will not get the proper answer. So they won't give you in the proper units, they will give you in different units. You need to convert into the appropriate units and then substitute them in the formula. So q into yi is organic loading in kg per day. So what is q? So generally q is nothing but the discharge flow rate in liter per day. This is mg per liter, so that is kg per day. So this is, we need to convert whatever the unit they give for the rate of flow, whatever the unit they give for yi, the BOD inlet. So you need to convert them so that you will get the output, the value of the q into yi in the kg per day. Volume we need to take, volume, V is the volume, here V is the volume of trickling filter. So volume of trickling filter, we need to take the volume of trickling filter in hectare meter, very, very important. So the surface area we need to take it in hectare and the depth we need to take it in meter. So hectare meter, the volume of the trickling filter is taken as in the units hectare meter and the q into yi. So q into yi by v is nothing but organic loading rate. So q into yi by v is organic loading rate or BOD loading rate. Okay. So q yi by v is organic loading rate. Organic loading rate in kg per day per hectare meter. So this is the unit we need to take. Either they will provide you directly the organic loading rate, or they will provide you the rate of flow BOD in and the volume of the trickling filter, or they may provide you organic loading and the volume of trickling filter separately. Any of the data may be given. So suitably you need to choose the appropriate formula for that, appropriate value and appropriate formula. And whereas F is called recirculation factor. F is called, here whatever the F we have taken, this is called recirculation factor. This is called recirculation factor. F is equal to 1 plus R by I by 1 plus 0.1 into R by I whole square. 1 plus R by I plus 0.1 1 plus R by I 1 plus R by I by 1 plus 0.1 into R by I whole square. So this is the formula of F, recirculation factor, where R by I is recirculation ratio. R by I is recirculation ratio. Okay, R by I is recirculation ratio. R is nothing but recirculated amount of effluent recycled, and I is amount of effluent applied. R is amount of effluent recycled and divided with amount of influent applied. So this is nothing but recirculation ratio. This is R by I, this is called recirculation ratio. There should be a difference between recirculation factor and recirculation ratio. You need to look into the question what was given. If it is recirculation ratio, then you need to put this in the formula and you need to find the recirculation factor. If recirculation factor is directly given, okay, then directly you can substitute that here. Okay, directly we can substitute it here. So you need to look into the question properly what was given in the question. If there is no recirculation, then amount of effluent recycled will be 0. If there is no recirculation, okay, for no recirculation, then R is equal to 0. Then F is equal to what? F is equal to 1. So for no recirculation, that means generally we don't do recirculation in standard rate trickling filter. In standard rate trickling filter, we don't do recirculation. Okay, generally high rate trickling filter, we do the recirculation. So that is why. So if it is standard rate trickling filter, default value of F is 1. Okay, default value of F is 1 for standard rate trickling filter. Whereas for high rate trickling filter, we need to take the value depending upon the what is the amount of effluent you have recycled back into the system. Okay, so using this we can design the filter. Designing of the filter means what? If you know the efficiency, so what is the efficiency you need to achieve? Okay, if you know that, we can find the eta. If you know the eta, from there if you know the eta, see here I know the eta because I designed. So I have a desired effluent BOD. So by there I can get eta. If I know eta, if I know Q, so Q is a known value because how much water is coming, how much sewage is coming, okay, into the system, that I can find easily. What is a BOD I know. So if it is a single standard rate trickling filter, then this is F is 1. So volume, finding the volume is nothing but the design of the trickling filter. From here we can find the volume of the trickling filter. So we will discuss some points are there about the trickling filter. We will discuss it in the next class, and we will go to the next treatment process also in the next class. Thank you so much.